Welcome to the Crazy Hat Chemist. So let's get started with another kinetics problem. Bam! So kinetics calculation number 3. I can't wait. So suppose you have 1.50 milligrams of a radioactive isotope tritium. Okay, that's a hydrogen isotope, by the way. It's the only isotope of hydrogen that is radioactive. How much remains after 300 years if the half-life of tritium is 12.3 years? Okay, since this is a radioactive isotope, all isotopic decays use first-order kinetics. The mathematical equations necessary all relate to first-order rate laws. Here are the integrated first-order rate law in yellow. That is natural log of x of t divided by x of naught is equal to negative kt. And the half-life equation, t of 1/2 is equal to natural log of 2 over k, where k is the rate constant, t is time. All right, got that. Note that 300 years is not a whole number of half-lives. Therefore, the table method that we used in one of the other previous lectures will not work. Okay, and so I'm verifying that right here. I've got the 300 years divided, the total number of years is 300, divided by the 12.3, that is the half-life time, so it's 24.39. That's not a whole number of half-lives, so the table method is not going to work out too well. So we don't want to do that. A graphical method will certainly work if you wanted to do that, but that is so much more tedious than actually using the integrated first-order rate law and its respective half-life equation. Certainly. Okay, so t of 1/2 is equal to natural log of 2 over k. This is the half-life equation for first-order kinetics. So what information do we have? We have the half-life. So we need to solve for the rate constant, which is k. So what we're going to do here is we're going to rearrange this equation and solve for k. So what I've done is I've rearranged the half-life equation and solved for k. K is equal to natural log of 2 divided by t of 1/2. Okay, so now I'm going to plug in the half-life, which is 12.3 years. So k is equal to natural log of 2 divided by 12.3 years. Okay, this will give me per unit time in per year for the rate constant. Okay, natural log of 2 is a number, 0.693. That's in your calculator here. And then you solve for the k. The rate constant k is equal to 5.64 times 10 to the negative 2 per year. Now you know the rate constant from the half-life using the half-life equation. Okay, now what we're going to do is use the integrated first-order rate law. So I have the k, that is the rate constant. I have the total amount of time, that's the 300 years. The question is the rate constant and the total amount of time in the same set of units of time? So that is years in this case. So one of them is per year, one of them is in years. They're going to cancel out, and that's okay. All right? And so again, the other information that we have is we're going to plug right into that equation here. We have 1.50 milligrams of a radioactive isotope. That is the initial concentration, and we are solving for how much remains after the 300 years, which is x of t. So we're going to plug all that information into that integrated first-order rate law. That's what I've done right there. So I've got natural log of x of t divided by 1.50, that's the initial concentration, is equal to 5.64 times 10 to the negative 2 per year, that's the rate constant, times 300 years. Notice that there's a decimal after the 300. That's letting you know that there are 3 significant figures and those zeros do count. Just to double check before you move forward here that the rate constant and the total time are in the same set of units, that they cancel out. That is one of those really initial mistakes that students make, is that they plug in the rate constant and the time and the units don't cancel out and they just keep on moving on, and then you're like wondering, scratching your head, why did I get the wrong answer? Units don't cancel. So now what we're going to do is we're going to get a number on the right-hand side of this equation, and we're going to get rid of that division problem with the natural log, and we're going to have a subtraction problem. And that's what I've done right there. So I've got natural log of x sub t minus natural log of 1.50 is equal to negative 16.92. That 16.92 is the product of the k and the t. Okay, now I'm going to get the natural log of 1.50, and I got that right here, and that is negative 0.405. I'm going to move that I'm going to move that negative 0.405 to the other side with an addition problem, and that's what I've got right here now. So now I got natural log of x sub t is equal to negative 16.515. Okay, I haven't done any significant figures here. I've just plugged in what's in my calculator. Now I'm going to ask myself, what do I do to get rid of the natural log? Because I'm solving for x sub t, that is the concentration or the amount remaining, in this case milligrams, at time t, which is at 300 years. So I need to get rid of that natural log to solve for x. So remember that e on your calculator is oh so critical. I'm going to take e to both sides there, and that's what I've done right there in that step. Okay, and now that will wipe out the natural log, and I'm going to have x is equal to 6.72 times 10 to the negative 8 milligrams. Okay, so that is the concentration or the amount remaining after 300 years. I would certainly hate to do this with the table method. The integrated first order rate law in combination with the half-life equation is so much faster in order to do this. Okay, I got a great hat for you today. It's Taco Tuesday. Give me a thumbs up if you like that video. Give me a thumbs up if you like tacos. And subscribe to my YouTube channel. Find me on the web, and you can find my entire website. Okay? I'll see you next time for more kinetics problems. Talk to you later. Bye now.